Thanks a lot for the invitation and for the opportunity to explain my work. So as you can imagine, there is a movie reference in this title. So this is, okay, this is not working now. Sorry, same thing happened again. Now it's working, okay. And that's maybe the good news. The bad news is that there will be no mention.
Need to share again.
Should I? It's not working?
No, we cannot see now.
Okay, let me do it again.
So Max, can you click on the arrow next to view?
Is it working now?
Yes. Yes. Sounds like from a different topic.
Good. Okay, so yeah, this is my take on this thing. And as I said, there will be no mention to the cobordism, sorry, to the multiverse in this talk. In this movie, the cast is given by these people: José Calderón Infante, who is now at postdoc at CERN, Matilda Delgado, Roberta Angius, and Jesus Huertas, who are my PhD students, and Adriana Macridou, who's a postdoc here at the IFT coming from Munich. And I will base my talk in several papers, probably too many, so I will try to cover some material, but I hope it's in a coherent fashion. So the plan of the talk is to talk about dynamical cobordisms, to explain that they appear everywhere, and to explain that they can appear all at once. And then I will conclude. So let me just start with some generalities about cobordism, and that's my movie picture take on them, which is saying that they describe an end of the world configuration. So the basic cobordism conjecture by McNamara and Baffa is that any configuration in a consistent theory of quantum gravity should admit a boundary, should be able to die, and that's because it cannot carry any global charges because it's a theory of quantum gravity. And this boundary can be sharp, as before, or it can be a fat configuration with many different ingredients and objects. Another view of the conjecture is that any two configurations in such theories must be able to be related by a domain wall. So you can imagine putting these two cobordisms to nothing together into a domain wall that interpolates between these two theories. Or it could be a kind of fat configuration which spreads over some distance, and you call this intermediate region the domain wall, which is kind of fat, not necessarily sharp. So there are many examples of such configurations. I will focus mainly on the cobordisms to nothing, and the typical examples are like for these sharp boundaries, like the Horava-Witten boundary of 11-dimensional M theory, or the configuration of orientifold 8 plus 16 D8 branes in type 2A theory, that is like half of type 1 prime theory. And examples with fat boundaries or fat end of the world configurations, there are many. For instance, if you take type 2B on a circle and you put some SL2 set monodromy on them, then you can have an end of the world given by a bunch of PQ7 branes so that you account for the monodromy on the circle. So let me now focus on what I will call dynamical cobordisms and what they are and why I think they are interesting. So the prototype example of this thing is the Witten bubble of nothing, which I hope is familiar to everybody, but I will just go through it anyway. So just take a d-dimensional theory, put it on a circle, and consider a theory with no fermions or fermions which are antiperiodic, so they break SUSY. And the point is that you have a vacuum configuration like that, which is just a pure compactification with constant radius, Minkowski vacuum, very nice. But this is typically unstable against nucleation of configurations like that, where you nucleate a region of nothing, which basically means that the circle is shrinking when the base manifold reaches this surface here. If you view this configuration from the perspective of the d-1 dimensional effective field theory perspective, it's just a boundary. It's a region where you cannot enter. And it's in this particular background, it's a region that expands in time. It's kind of cosmological situation where the whole universe eventually decays because it's eaten up by this expanding nothing. So some of the properties that will be useful to generalize this to our setup, some of the properties of this Witten bubble of nothing are that from the perspective of a lower dimensional theory, there is some scalar, which is the breathing mode of the circle, which is running in one dimension. That is, as you approach this bubble of nothing, and it goes to zero size when you reach this boundary. Because it's a circle compactification, the scalar potential is 0, so it's a particularly simple setup. There is a singularity from the perspective of the lower dimensional theory at finite space-time distance, which is where the circle is shrinking. It's a region that you can reach or that it reaches you because it is expanding. This singularity is just an artifact of the effective field theory. In the full theory, the whole configuration is nice and smooth, okay? And the scalar, from the lower dimensional perspective, reaches an infinite field space distance because it goes to exactly 0 size. So if you measure it with the metric that you get in the moduli space of the circle compactification, this is at infinite distance. In fact, the fact that you get this singularity in the geometry is because the back reaction of the scalar becomes very large, because in a finite space-time distance, it is traversing an infinite field space distance, okay? But again, you shouldn't worry about these infinities because in the UV, everything is well-defined. It's only that from the lower dimensional perspective, there seems to be some codimension 1 configuration that ends space-time, that we will call in general end of the world brane, okay? And as I said, in general, this is a time-dependent configuration. So our take on generalizing this idea, and this is what we will call dynamical cobordisms, is to consider solutions where there is some space-time dependence for the scalars, some of the scalars, such that they reach infinite field space distance at some codimension 1 singularity of the metric at finite space-time distance. And at this location, the cobordism defect, whatever ends the space-time, which we will call the end of the world brane, is sitting. I call it cobordism defect because this is what is predicted by the cobordism conjecture, that there should be boundaries. So this will be whatever objects you need to include a boundary in this theory. Some small differences with respect to the Witten bubble of nothing example is that we will work for general scalar potentials. So in principle, we don't assume we have an exact moduli space or whatever. We include the general scalar potential. And most of our examples will be static. Okay, we do have some more complicated examples with time dependence or whatever, but mostly they will be static. This asterisk here is because when we talk about distance and finite distance, you have to be specific in which frame. So we will continuously work on the Einstein frame of the lower dimensional theory. Okay.
May I ask a question?
Sure.
So what is the motivation in this definition for the infinite distance in the scalar field? So in this particular example of Witten's bubble of nothing, it is a case, yes. But in general, when you define this dynamical cobordism,
yes,
why did you want to scalar field to go infinite
Our
distance?
take is that this is kind of empirical and exploratory. We find many examples that behave like that, but we don't claim that this is a theorem. I have some disclaimers about this in a couple of slides. Okay.
Thank you.
Let me disclaim, and then maybe you can ask again. Okay. Okay, so this is the picture. And basically, our take on this dynamical cobordism is that at some finite space-time distance, there is some scalar which is going to infinite distance. The kinetic terms become large and back react, and they develop this space-time singularity. So basically, the scalar would say that at their signal, you unleash hell. Okay. So there are many examples of this, I will make the disclaimers later. Let me just continue a little bit with some kind of universal description for all these examples and in what particular setup they hold. So basically, we start with some theory of gravity and a scalar, just a single scalar, could be a combination of several, in some d-dimensional theory with some general potential. It could be 0, that's also included, but it could be any general thing. Okay. And then we consider solutions which run in one dimension. Okay, so there's a warp factor in this direction y, and the scalar is a general function y. And then we demand that this scalar reaches this infinite distance field space at finite space-time distance, so at the point y equal to 0. So there are many examples of this, but they become like very similar to each other if we zoom into this y equal to 0 region, so very close to this end of the world brane. This is what we call local dynamical cobordism. And I will describe most of the examples in this local limit, even though for many of them the full solution is known, even away from the end of the world brane. Okay. In this local description, there is a very universal form of the solution in terms of just a single parameter delta, which tells you how different quantities diverge. So the scalar diverges like a log with coefficient controlled by delta, and the warp factor also in a similar way, in a way that also depends on the dimension. The potential could be 0, but we allow it to depend also on this the general function of this phi, and it behaves exponentially, again controlled by this delta. If the potential happens not to diverge in the way, it means that the coefficient of this potential is 0, and then there is some specific value for delta in that case, which corresponds like basically to 0 potential. And there are some scaling laws that relate the space-time distance, the field space distance, and the curvature in this way, which tell you that when the space-time distance goes to 0, then the field theory distance diverges, and also the curvature diverges. Okay, and we have many examples that correspond to different values of delta. This is just a table, and I will just present some of these examples in a little while. So before that, let me go to the disclaimers. So the first one is that not all the cobordism solutions, all the cobordism solutions of the equations of motion, all the cobordism configurations in string theory are of this kind. And the simplest example we already mentioned. For instance, if you take the Horava-Witten boundary in M theory, there is not even a scalar to talk about. Okay, so clearly there is no running scalar, and it's not divergent or going to infinite distance. It's just a boundary. Okay, so many cobordism solutions presumably are not of this kind. Okay. Another example, again, is like half of type 1 prime theory, which is just the negatively charged orientifold plane with 16 D8 branes on top, as counted in the double cover, which corresponds to an end the boundary for type 2A theory in a configuration with constant dilaton, constant warp factor, just the boundary of Minkowski space. Okay, there is no running scalar at all. So again, not all cobordism solutions in string theory are of this kind. Okay. And of course, not all solutions with varying scalars are cobordisms, right? If you take a wave of some scalar which is passing through flat spacetime and perturbing it a little bit, of course, this doesn't lead to any destruction of spacetime or whatever. Okay, so our statement is about configurations which contain scalars which run and reach infinite field space distance and at finite spacetime distance at the codimension 1 singularity. And it will be for these configurations that I will be discussing. And these are what we call the dynamical cobordisms. And I have an asterisk here, because even for those, there is some small subtleties, because as you can guess, going to infinite distance in field space implies that you have a lower cutoff, and there could be subtleties about what happens if you just use effective field theory. Okay, so these are my disclaimers. Let me see if there is any question about this.
Can I quickly ask, Angel?
Sure.
Would there be a story for higher codimension, even though this is not what you've explored, would there be a story for higher codimension guys as well?
Yes. I will mention them, but I will reduce them to codimension 1.
Okay.
Okay. So at the end of the day, they will be codimension 1 for the purposes of this talk. Okay. More questions? I mean, I guess you're thinking about the small black holes, and there will be a discussion of a small black holes. Yes. Good. So let me just move on and discuss why this kind of dynamical cobordism appear everywhere. Well, everywhere in many examples, many large classes of examples. Okay, so first one is something like that similar to something we discussed is a massive type 2A theory. So if you take 10-dimensional type 2A theory with some mass parameter M, which is this 0-form field strength flux, you have some effective action which contains some potential for the dilaton. Okay, so you don't have maximally symmetric Minkowski vacua, but you have to consider domain wall vacua in which some scalars run. In fact, the running solution is given by this. This is like the back reaction of a D8 brane, it's sometimes called the domain wall solution. And there is some scalar, which is the dilaton, which is running, and there is a warp factor, which is also running. They run linearly, things run linearly with this harmonic function, which is the solution of the harmonic function in 1 dimension, which is like the codimension of the D8 brane, which kind of creates this background. There is a singularity when the warp factor goes to 0, and it is at finite distance in the Einstein frame, so you can compute it, and you can see how the scaling properties behave. And this typically corresponds to the dynamical cobordism, where the spacetime ends, and you have to add some orientifold plane and a suitable number of D8 branes to absorb this flux before this spacetime can end. So this is more or less the Polchinski-Witten story of type 1 theory. That is, when the dilaton grows large, you have to cut off your spacetime, adding some orientifold plane and D8 branes. Okay, and this has this solution behaves in the way that I described with this end of the world local model, with some particular value of delta, which you can see is related to the exponent that you get in the potential here for the dilaton. Okay, there is a square root of 2 which mismatches, but has to do with how you define the distance in field space. That's one example. Another example, which is more exotic, but historically it appeared very early on, has to do with the 10-dimensional non-supersymmetric USP32 string, the Sugimoto theory, which is obtained by taking type 2B and mod it out by some orientifold and adding a positively charged orientifold 9 plane. So that means that to cancel the Ramon-Ramon charges, you have to add 32 anti-D9 branes. So it's a cousin of type 1 theory, but in a non-supersymmetric fashion, because this orientifold plane and the anti-D9 branes preserve different SUSIs. If you compute the effective action, there is a dilaton potential because the Ramon-Ramon tadpoles cancel, but the NSNS don't. So you have some cosmological constant, which actually is a field dependent. So it depends on the dilaton. So it's a potential for the dilaton. And you can build running solutions, as was done by Dudas and Murad almost more than 20 years ago, in which the scalar is running in one direction y, and then there is symmetric, which is back reacted by this varying scalar in this particular way. So it's a codimension 1 running solution. And there are singularities at 2 points, which in their coordinates, they were y = 0 and y = infinity, but they were at finite distance. So you can go to normalized coordinates, and then you can see that they sit at some finite distance, and there is a finite interval in which this theory is living. So again, you have the idea that this cuts off spacetime, which is something that Dudas and Murad already proposed. Now we are just dressing this into a more general picture of this dynamical cobordism and the cobordism conjecture. So again, this kind of running solution locally behaves as one of these local end-of-the-world brane models with some particular value of delta, again, related to the scalar potential for the dilaton. And the novelty here, compared with the type 2A theory, is that there is no microscopic description for this end-of-the-world brane, okay? Which is a familiar phenomenon because this theory is chiral, and it's not easy to put boundary conditions on theories which are chiral, okay? But again, the proposal is that these singularities behaving in this way, some scalar goes to infinite distance in some finite spacetime distance, define that the spacetime is ending there at this singularity. So it's not that this singularity is resolved and then you go on moving, but rather that space is cut off at this location. Okay, and there is many work on this Sugimoto theory, compactifications thereof by many people. So I put in some references, but probably there are many others that I'm missing. So apologies for that. So let me mention other examples which have to do with compactifications. One of them is basically the Klebanov-Strassler throat. So let me start thinking about ADS5 times T11. Okay, and consider, this is starting with ADS5 times T11. T11 is just S2 times S3, and is the 5-dimensional base of a 6-dimensional Calabi-Yau threefold, non-compact Calabi-Yau threefold, which is the conifold. This geometry with n units of Ramon-Ramon 5-4 flux is the near horizon limit of n D3 branes on the conifold, and this is the Klebanov-Witten theory. I will just describe the gravity side of this. Since you have this S3, this 3 cycle, you can add m units of Ramon-Ramon 3-4 flux on this S3, and then there is a solution by Klebanov and Seidlin where you see that the T11 geometry runs in the radial direction of this anti-de Sitter 5 with the Minkowski slicing, such that it shrinks at some singularity, which is at finite spacetime distance. This singularity is not very nice, but it was smoothed out by Klebanov and Strassler by realizing that actually the S3 is capped off, has a finite size and caps off the spacetime at some infrared scale or coordinate in your geometry. And that's the Klebanov-Strassler solution. So you can view this story as a dynamical cobordism from the perspective of the 5-dimensional theory, in which you have things that run in 5 dimensions. In particular, there is this NSNS scalar, the integral of the B field over the S2, which is running in the radial coordinate. And this basically takes care of removing the 5-4 flux out of the configuration. And at the same time, the volume is running also very slowly with a log until you hit the singularity. By the time you hit the singularity, all the 5-4 flux has disappeared, and then you can shrink it and recover one of these singularities where some scalar, which is the volume, is like reaching infinite distance, And the model is locally described by one of these local end-of-the-world theories with this value of delta. Of course, the singularity is not the full solution. Again, in the ultraviolet, there is nothing to worry about. The full solution, the ultraviolet resolution of that is the Klebanov-Strassler throat, where actually the singularity is smoothed out, and what you have is a finite size S3. That's something that you don't see in the effective theory upon compactification on this 5-dimensional compact space. Of course, let me just make another disclaimer. I'm not claiming here that there is a scale separation and then I have a reasonable effective field theory to describe my 5-dimensional anti-de Sitter. Okay, so if you want to think about it, what I'm doing is kind of truncation along this S2 times S3, which is has a lot of symmetry. So I'm just truncating to the invariant sector. Okay, but I would agree that there is no scale separation, and it is questionable to argue whether this effective field theory makes sense as an effective field theory. It's only a matter that I'm looking at the sector that doesn't activate the Kaluza-Klein modes. Okay. Good. Next example are within bubbles of nothing are related examples, which are from this perspective of local model can be described in the following way. Imagine that you take flat d-dimensional space and you slice it in such a way that you have a radial coordinate and some angular sphere in this way. So you have n flat coordinates, and then in the remaining d-1, you separate the radius, and then the d-n-1 dimensional sphere. Okay, so this would be the flat space, and then I'm just slicing things in here. I can regard this as some compactification on the sphere where the size of the sphere is running as you go towards the origin, where the circle shrinks. Okay, so if you do that, well, the potential in general is non-trivial if you compactify more than one dimension. In the Witten example, it was just S1. And then if you do this exercise, you can see that locally the tip of the of this configuration is described by one of these end-of-the-world brain models with some particular value of delta that depends on how many dimensions are in the game. What's the dimension of your sphere? And of course, in here, I mean, one should remember that our picture is not really a cigar. The sphere doesn't have an asymptotic constant value, okay? It really goes like that. So the asymptotics of this configuration looks crazy, but remember that we are just trying to describe the local behavior near the tip of this bubble of nothing, okay? So this is precisely, for instance, this is precisely the behavior of the Witten bubble of nothing near the tip, okay? So one could imagine that locally you have this kind of flat space with crazy asymptotics, but in a full solution, beyond the local approximation, let's say, this circle goes off to something which has a constant asymptotic radius, okay? So that is our picture. We're just describing the local configuration. Good. Another example of this very simple kind is to add defects to absorb the fluxes on these sphere compactifications, and that's described locally by just taking d-branes in flat space and just slicing it with respect to the angular coordinates. So we have a d-brane sitting in some transverse flat space, and then the transverse space we regard as a compactification on a sphere, now with some flux, which is just the charge of the d-branes, which creates some flux on the sphere that surrounds it. Again, there is a non-trivial potential for the size of this scalar coming from just the curvature if you have a higher dimensional sphere, and also from the flux, and also there is a running dilaton. If you put everything into the game, basically you recover that locally you have one of these end-of-the-world brain models with some particular value of delta that depends on the dimension of the brain, okay? So this works like a dynamical cobordism, as I was mentioning, except for the specific case of p = 3. Okay, p = 3 is a little bit special, and the reason is that for p = 3 for a D3 brain, actually when you approach the D3 brain, well, you get some anti-de Sitter throat. Okay, so it's not really a dynamical cobordism. So space-time is not ending there in a sense because there is some anti-de Sitter throat, which doesn't have a finite size, if you wish. Okay. And also for the p = k, so for the D2 brain, there is some surprise which is hiding, which is interesting. And later on, we will discuss related examples. So maybe we can postpone that. I mean, sometimes there can be surprises from the ultraviolet, and we will discuss them in a little while. Okay, another example, which is kind of similar, is to consider these are the IFT strings introduced by Martesano, Martucci, and Valenzuela, where they were considering 4 d n = 1 theories, and they were looking at string-like solutions in these theories, which are defined by the fact that there are some actions that shift by some quantity when you surround them. And they saw that the actions, which are partners of this, they diverge when you approach the core of the string. And they were making very interesting connections with the distance conjecture and the RG flows as you move away from the brain. So some of these statements you can translate to our language by playing this game of regarding the transverse circle as a compactification. And now the action shift here corresponds to having a one-form flux on this S1 compactification. So if you play this game, you have a dictionary between the two pictures, and you can find what's the delta, the value of delta of this parameter for the local end of the world brain description of this tip here. So it's interesting to make the connection between these two approaches. This is one of the examples that Miguel was kind of mentioning at the beginning, where you have some singularity, which is at a higher codimension, because this is codimension 2 in the 4D solution. But in examples like that, we always like compactify on the transverse angular coordinates such that we end up with something which is codimension 1. And we can regard it as a dynamical cobordism at codimension 1, as I was defining them at the beginning. And a similar game you can play with small black holes. Again, small black holes, they correspond to singularities, which occur now in codimension 3, okay, and in 4 dimensions, okay. And they're very interesting tools to probe infinite distance limits, as was done by these people and by many others afterwards. So just to review a little bit the structure, we start with a 4D theory with some scalar and some U1 with some dilaton scalar dependent gauge kinetic function. And then for this kind of situation, you can build a black hole in which the scalar is running, evolves in the radial direction, and then blows up at the singularity. I mean, these things have a horizon, but it has 0 size, and the scalar is blowing up at that point, reaching infinite distance at the point which is at finite space-time distance. So we play our game of compactifying the transverse spheres, and we can regard all these configurations as dynamical cobordisms of the resulting two-dimensional theory. And they have some corresponding value of delta, but because the lower dimensional theory is two-dimensional, there is no Einstein frame. So there is some kind of frame-dependent quantity here that we introduce here. Okay, but otherwise the story is very similar, and it is interesting. We will discuss that later on. Let me describe another example.
Angel, can I make a question?
Sure, yes.
So you're showing many different examples with different values of this delta. I'm wondering, do you have any intuition or explanation for the different values of delta? Like, for example, in the distance, the different exponential rates give you information about the nature of the tower. Can you say something if I give you to get a particular delta?
It would be very interesting. I cannot say anything meaningful. We don't see any pattern. We don't see any specific property, at least not so far. Okay, but it is interesting, and we have tried to think about it.
And for the case of the EFT strings, you saw that it's the same value of delta for all of them, like.
Yeah, it's very tricky. That has to do because in the EFT string, sorry, in the EFT string, the delta that you get, actually, so when you compactify down to 3 dimensions, basically there are now 2 scalars: the original scalar, the suction that you have in 4D, and also the circle. So this delta actually is controlled by who is going to infinite distance first, or more quickly, and it is the circle that goes first. So this delta is just controlled by the fact that you're compactifying and that the compactification is shrinking. So basically, the UV completion of this local end of the world brain model in 3D would tell you that you have to go to 4D, and then in 4D you would see the things that you were seeing, that at the core of the string you have these other behaviors, and this other scalar is going to infinity, and then you can probe different infinite distance limits, and that can be sensitive to which is the suction that is going to infinity. But in our description in 3D, we don't see that. We just see the compactification.
So here you lose the information of the Keller potential, right? Like the type of...
Basically, yes. Yes. It would be in the UV of the description that we take, yes. More questions? Okay. That's a good example that sometimes the local model misses part of the information. So let me go to another example where the local model is not perfect in the sense that it misses information. And that has to do with double holography. So let me just give a quick overview of what will be useful for me in double holography. So imagine that you have a 4D CFT, which is defined on a half space. That is its Minkowski 4, but chopped with some boundary. And then on this 3D boundary, you couple some three-dimensional conformal field theory, which we call a boundary CFT, BCFT. Okay. And if the 4D CFT and the 3D BCFT have a gravity duals, then you have a gravitational dual of this configuration, which is the dual of the CFT. I'm already assuming this will be some kind of anti-de Sitter 5 if this is a true CFT. And then the dual of the 3D BCFT will be some anti-de Sitter 4, which means that if you take the anti-de Sitter 5 and slice it in anti-de Sitter 4s, there will be some evolution of this anti-de Sitter 4 as you move, and suddenly it will stop existing because there is nothing on the other side. So the gravity dual of the 3D BCFT is an end-of-the-world brane, some kind, for this kind of anti-de Sitter 5 bulk dual to this 4D CFT. Okay. So these kind of anti-de Sitter 4 branes, they're called sometimes Karch-Randall branes, and they have localized anti-de Sitter 4 gravity. So there is a graviton independent for the bulk graviton, which is propagating here, and that's basically because this is the gravity dual of the stress energy tensor of the 3D BCFT. So it's a very interesting story where there are these two holographic duals, and that's the reason for the name double holography. Okay. And another interesting bit is that this is a higher dimensional version of what people have been doing in the quantum island, or and still doing in the quantum island program in the lower dimensional theory. And people are attempting to make similar statements for other things. So basically in this picture, there is a gravitational sector which is living on this end of the world brane because there is dynamical gravity, because there is this localized gravity here. And then there is this thermal bath, which is non-gravitating, which is where the Hawking radiation of whatever is here, black hole or whatever, is escaping. And then you can try to compute the properties of your gravitational system by looking at properties of the Hawking radiation captive here.
Angel, can I ask a quick question about the setup?
Yes.
So in the graviton on the ADS4 factor, from supergravity point of view, is some sort of like zero mode of the 5-dimensional graviton, right? Which is localized, and that's
I will have some explicit example where this is realized. So at the moment, this is like bottom up, where you just put this brane and then you claim that there is a localized graviton here, more or less. But there will be an explicit example in the next slide. Okay. And then you will see where this other graviton is coming from. And then you can ask me again if it's not satisfactory. Okay. So there is a very specific example of this by taking 4-dimensional n=4 superjam mills on the half space, and then you take a specific 3-dimensional boundary conditions defined by some 3D n=4 boundary conformal field theory, something which preserves half of the superconformal group of this theory. Okay, so technically the supergroup is OSP 4/4, and this was proposed by Gayotto and Witten, and they classified all these boundary conditions, or at least large ones. And in particular, they also provide a specific realization of this in string theory, where the 4D n=4 superjam mills is located on the D3 branes, which are now semi-infinite in a Hanani-Witten-like fashion. They are ending on configurations of NS5 branes and D5 branes along these directions, if you want to be super specific. It's like in Hanani-Witten, if you're familiar with the setup. Okay, now there is a gravity dual of this configuration because it has a lot of isometries and a lot of supersymmetry. The gravity dual are a bunch of possible geometries with isometry group SO2, 3, which is the conformal group of the anti-de Sitter 4 part, times SO2 times SO2, which are the isometries preserved by these D branes. This is the subset of SO6, which is preserved by these boundary conditions, by these 5 branes. And there is a bunch of people who work on these configurations, their interpretation in terms of branes ending on branes and applications to different setups, even to the Swampland. Okay, so the solutions for this are explicitly known, and the map to the different branes is totally known. Okay, and the configurations in a more specific way look like that. Okay, basically you have a vibration of ADS4 times S1, times S2 times another S2 over a Riemann surface. There is a Riemann surface is just this quadrant here. Okay, so there is nothing outside. Basically, the S2 times S2 are fibered in such a way that one of the S2s shrinks at this line and the other shrinks on this line. So if you take these lines here, these arcs, one of the S2 shrinks here and the other S2 shrinks here. So overall, you have some S5. Okay, and if you take this anti-de Sitter 4 and this radial coordinate here, and you go very far away from this tip, you recover anti-de Sitter 5. So you recover anti-de Sitter 5 times S5 with the flux and everything. these punctures here, these are poles and things like that, and they correspond to the locations of the brains, basically, these 5 brains. And these parameters, the location of them corresponds to parameters like how many D3 brains are ending on which particular 5 brain. Okay, so it's a very explicit map. The point now, the picture is that asymptotically you have ADS5 times S5, and as you come close here, you start seeing all this structure of 5 brains and all the information. And the 5 brains, because they carry F3 and H3 resource, F3 and H3 fluxes, they are able to little by little start removing your end units of 5 from Ramon-Ramon flux, so that by the time you get here, basically all the flux for D3 brains has disappeared, and you can safely shrink your S5 and end into nothing. Okay, so that's the picture. I didn't write down the full solution, but that's the intuitive picture. The full solution will be something like that. There is a bag like that, which is like ADS4 times some basically almost compact X6, and then there is a spike which sticks out of it, which has a structure of ADS5 times S5. So answering your question, Miguel, the graviton in 4D is coming from this compactification on X6, basically. Okay, and there is a weak coupling with the anti-de-Sitter 5 graviton here in the back, which has to do with the structure of this neck.
So Angel, can I ask, in this picture, I should think of the horizontal axis as the coordinate that, that was also horizontal 2 slides ago, right? The boundary coordinate that goes to the boundary?
This corresponds to the thing that was very far away from the origin. So this picture is a little bit simplified. I don't know how to draw it better, but this is really heuristic. I didn't attach any meaning to the things I'm drawing here in the sense of particular directions. Okay.
Angel, this is a UV brain, right? From the perspective of the ADS, I can think of this as an ultraviolet brain, or is it incorrect in the Randall syndrome language?
It's not really correct. It's not like Randall syndrome in the sense that the real picture is this one. Okay, so the brain that we're introducing also intersects the holographic boundary.
No, I understand, but if I ignore the holographic boundary, I just look at a piece of the black ADS4 brain. Is it a detuned UV brain where the tension is a little bit too small to be flat, so it is actually ADS4?
Yeah,
you know, I take Randall syndrome and makes the tension a little bit smaller. I think that would be that type of brain.
Yeah, maybe you can think about it that way, yes. Yeah, I understand what you mean. So you want to mismatch the tensions of the brains with the cosmological constant in the middle and perhaps allow some more general for the geometries beyond Minkowski, right? That's possible, yes.
I have a question. In what sense is the gravity localized on ADS4 graviton?
It's okay. Maybe I can go a little bit later. Basically, there is a 0 mode for the compactification on this X6, let's say.
0 mode.
And then there is the bulk graviton, and of course they couple. So at the end of the day, there is only one graviton which is massless and another one which is massive.
So let me just, it's a bit surprising. There must be some misunderstanding. Suppose I take the limit where one of the ADSs become non-dynamical. By that, I mean that if you're thinking of ADS4 sitting in ADS5, and I want to take the limit as your central charge in your bulk theory to be huge, but your boundary theory to be small. In that case, wouldn't you have said that you have a gravity theory in lower dimension which interacts with no graviton because M Planck of the higher dimension has gone to infinity?
I think so. There is such a limit that one can take in these geometries, and now you have a picture of what happens. Basically,
but you're saying that the gravity does not live everywhere anywhere because that limit would have M Planck infinite. Am I wrong?
Sorry, this limit would have?
I'm just saying that there would be a limit then, it seems to me, that you would have a strange situation where you would be saying, I have a defect of some kind in a space-time for which the gravity lives, and in the bulk, you have decoupled gravity because M Planck is infinite or something.
Yeah, okay. So you mean that maybe this is a pathological limit or something like that?
Yeah, no, just the same way we talk about the low energy limit of effective field theories where gravity is irrelevant. You could have done this for this lower dimensional gravity theory.
Yes.
And that would be bizarre. You'd be saying that I have a gravity in the X dimension which sits in an X plus 1 dimensional space which is no graviton or no weakly coupled. So weakly coupled you can ignore it.
I think if you do this limit carefully, I think basically all the anti-zeta 5 decouple, so it kind of disappears and you don't talk about it basically. Maybe that will solve what you're asking.
When you say the graviton is localized, you're saying there's a wave, there's a scale?
Yeah. Well, the scales here are a little bit crazy. Okay, so there is a scale that defines the size of this bag here, and then
So
there
you,
is
you really claim that there is a spin 2 massless mode stuck on that, on a particular brane?
Yes. But of course there will be plenty of other stuff at similar scales. Okay, so I don't mean that there is a decoupling or this. Okay.
But Angel, as you were saying, it couples to the bulk mode, so in the end there's one massless combination and another is massive, yes?
Yes.
Oh, so there's only one massless which propagates in the bulk.
Yes.
So there's not
basically
two.
the fact that the graviton here, that there is a mass for the graviton at the end is because the graviton here is dual to the stress energy tensor in this three-dimensional boundary field theory, but this of course talks to the 4D CFT. Okay, so there is a leaking. And
so there's no massless graviton on ADS4.
Yeah, not exactly massless. It is massive.
Yeah. Okay, that's what I was
basically. It's massless in a limit, but it's a limit in which the ADS5 disappears totally from the picture, right? Okay.
Yeah, I just wanted to comment that, yeah, it's common in boundary CFTs that you don't have a well-defined 3D stress energy tensor. You know, basically, if you expand out, you know, like there's no well-defined OP that's only in terms of like 3D operators.
Yeah. Yes, this is, I think,
that I will discuss in a second.
Well, this is consistent with the fact that we still don't have a stringy realization of these Randall's scenario, Randall-Sanders scenario.
Yes. I'm confused. I have a simple question. If you look at this picture where I see the blob, which says ADS4 times X6, right? I could think of this as being a compactification on the Calabi-Yau to 4D, and I could think of the throat that sticks out as being a stack of D3 branes, right? I mean, I can't. And then it
only that the geometry is not with a Minkowski slicing. I understand what you're asking, and it's more or less like that, but it's not that the slicing is Minkowski. It's not like in the Berlin picture.
No, I understand. It's not Minkowski, but it's a quantification to ADS4, not to Minkowski.
Yes.
It's of course a non-scale separated compactification, but I can still think of a non-scale separated compactification which goes to ADS4, and then in that X6 there's a stack of these three branes which produces the throat that you show, and that's perfectly together with having a proper gravity theory in this ADS4, right? I mean, of course, given no scale separation.
Yes.
Okay, thank you.
Let me move on a little bit because I have to move on. Okay, so let me just mention something. In this picture, the local model, the local end of the world brane that I have been using, describes only the shrinking of the phytosphere. So to describe the 4D graviton that we're discussing, you have to take the whole bag. Okay, so that's an end of the world brane which is not well described by just the local model. And I wanted to mention that there is this double sum scaling limit that we discussed with my student Huertas, in which basically we made this graviton massless and we decouple this thing. And this is the gravity dual of just forgetting about these half semi-infinite D3 branes. So your field theory now is a bunch of D3 branes suspended among 5 branes, and that's a 3D field theory, which is now is not the boundary of anything, okay? And it has a 4D ADS4 gravity dual. So this should correspond to the limit where the 4D graviton is massless. It's just a different holographic pair, basically, okay?
Excuse me.
Sure.
Yeah, in this case, you mentioned is the case in which you put a cutoff brane and basically you get a compact internal space with respect to the ADS4, right? So in this case, you have a massless graviton on ADS4 when you put a cutoff brane and you decouple ADS4 across.
Oh, a cutoff brane, you mean in the ultraviolet, like away from the holographic boundary, you mean?
Yeah, I mean, you have, because in general, the solution does not have a compact space. And this is probably the reason why you have problem in localizing gravity on ADS.
Yes, sorry, in this limit, basically you shut off the anti-de-Sitter 5 piece, and then there is, it really is compact, right?
Okay, so you cannot, for example, extract ADS5 in some asymptotic limit in...
Of this? No, you have got rid of all of the anti-de Sitter fives in this, at least in the way
Okay,
we were
thanks.
doing it. Okay.
Okay,
Perhaps you can
thanks.
do something different, but okay, more questions. Okay, so these were a lot of different examples, and you can see that I feel kind of haunted by this dynamical cobordisms. So I feel a little bit like that. So let me move on, because there are so many examples. We proposed some version of something that we call the cobordism distance conjecture, which is basically saying that every infinite field distance limit in effective field theory, an effective field theory consistent with quantum gravity, should be realizable as some dynamical cobordism running into some codimension 1 end of the world brain in the theory. Okay. Now, one thing that I want to mention is about the caveats of this whole discussion I've been doing, and has to do with the fact that we are all the time discussing the scalars that go to infinite distance in field space, and then in these setups, the distance conjecture implies that you have a lower cutoff. So one should be careful, and in particular, you can relate the lower cutoff with whatever the field theory distance. So when it goes to infinity, it goes like that. So this is the distance conjecture, and you can relate this to the space-time distance. So when the distance goes to 0, the distance to the singularity, the cutoff is also going to 0 very quickly, and also the curvature is blowing up, so higher curvature corrections will become important, and that it's clear that you shouldn't trust effective field theory in this setup. So the question is whether higher curvature corrections can modify this picture, because you're reaching basically your cutoff, your species scale of your effective field theory. Okay, so let me discuss this for a second and see how the theory can evade situations where you were thinking you were shooting towards infinite distance, and then the theory can kind of dodge and evade this dynamical cobordism, if you wish. One class of examples is obtained by looking at small black holes. Okay, so the typical small black hole story having to do with these higher curvature corrections is that they have 0 area at the 2 derivative level, but if you include higher curvature corrections, they develop some stretch horizon and some finite entropy, and we know from the Swan-Lamb discussions that this stretch horizon should be of the order of the species scale. Okay? From our perspective of compactifying on the sphere that surrounds the black hole, regarding these black holes as dynamical cobordisms, so in 2 dimensions there is something running, some scalar running in codimension 1. Basically, what this means is that instead of hitting a singularity, which is the 0 area horizon of the small black hole, because now there is a stretch horizon, you run into some near stretch horizon geometry, which is ADS2. So instead of finding some end of the world, you're finding some ADS2 with size the same as more or less the size of the 2 sphere, which is like the species scale size. Okay, so this is a correction of this dynamical cobordism picture by the appearance of some UV physics having to do with the species scale. Okay, so this is also some reinterpretation of what we did regarding the species scale, relating its role in higher curvature corrections and the size of the smallest black hole that we developed with Jose and Matilda, in particular for some classes of small black holes and also for the D0 brains in 10 dimensions. We were seeing how this game was played and how the species scale appeared in all of these different avatars. What I'm presenting here is that this implies that there can be corrections at the species scale for this dynamical cobordism picture that I have been discussing. So one should be aware of that. Okay, in some cases they may appear, in some other cases maybe they don't, and then you have a well-defined end of the world. It's an information which is not in the effective field theory, it is in the UV theory. Okay, so one should be aware of that. Okay, let me just discuss another situation in which one can have physics that corrects these small black holes, but which is not coming at the species scale. It's something a little bit more exotic and has to do with the following. Imagine that you have a general black holes could be large in some theories with some scalar potential. Okay, then you have a black hole attractor potential that is pushing the scalars towards the attractor value at the horizon of the black hole, but very far away from the black hole, the 4D potential is fixing the scalars at some other value, which could be different from the one at the horizon. Okay, so there's a competition between these two effects. It was studied for a particular effect that they were calling explosions by Silverstein and collaborators, and in a language much closer to n equals 2 supergravity in 4 dimensions by Ferrara and these collaborators. Now let me just bring this story to the case of small black holes. So for small black holes, there is some black hole attractor potential, which is pushing the scalars to infinite distance at the singular core of the black hole. And the 4D potential at asymptotic infinity is keeping the scalars fixed at a finite value. So there is some running of scalars as you move. So again, there is some competition between these two effects. And in this case, there can be some mutual consistency conditions of small black holes and 4D potentials for each infinite distance limit. Okay. So if you take the 4D potentials that we have been using, which are exponential, positive exponentials with the parameter delta in here, and you take the black hole attractor potential for the small black holes, which goes something like that, there is a competition of these two exponentials. What matters is the product. And that means that if you have some 4D potential, which happens to blow up at infinity in field space faster than some small black hole potential, then that means that it costs too much energy to send the scalars to infinity as the black hole would like, because it has a lot of cost at the level of the scalar potential. And then the small black hole solution doesn't exist, so the black hole basically explodes. It has to become large because it cannot exist at zero size. There is not enough energy to keep it zero size. Okay, that's interesting because it's a failure again of dynamical cobordism, because now the black hole is large, but it's not at the species scale. Okay, because this thing can explode to any size, could be microscopic or even run away to infinity. So it's something a bit pathological. So then what we propose is that there should be in any of these theories with scalars and general potential some small black hole criterion, which says that for each infinite distance limit, at least some small black hole should be able to remain small despite the competition with the 4D potential. So that it still can define the species scale as the size of the smallest black hole, okay, which would be the stretch size of this black hole, which is at the species scale. Okay, and we applied this to several theories. And interestingly, if you take 4D n=2 theories, okay, and gauge supergravity or whatever, and if you focus on the limit where you send all the moduli to infinity, basically you recover this condition for the Keller potential of the vector multiplets of this theory. And at no point you introduce the ultraviolet information that this is coming from a Calabi-Yau compactification or whatever. So it's a bottom-up Swampland derivation of this Calabi-Yau property, which I think it's a fun story. So that's why I wanted to mention it. Okay, it is this small black hole criterion ensuring that at any infinite distance limit, any possible conceivable potential you can introduce by gauging supergravity or whatever should not be able to kill all the small black holes. At least some should remain small. Good. Any question? Okay, so I should be finishing. So let me just go to the last part, which is when dynamical cobordisms appear at once. And the idea is to consider intersecting end-of-the-world branes, which would look more or less like this. Okay, basically, considering intersecting end-of-the-world brane configurations can have several interesting interpretations from the perspective of, let's say, the cobordism conjecture. One of them is that if you consider some configuration with some end-of-the-world brane like that, some configuration of quantum gravity ending into nothing, this configuration itself should admit boundaries itself, so things like that. So there should be a configuration where two different end-of-the-world branes meet. Another take on what these intersecting end-of-the-world brane configurations mean would be to consider this opening angle between the branes and to enlarge it so that you have this picture. Then in this interpretation, what you have is a defect on the end-of-the-world brane, which turns one kind of end-of-the-world brane via some kind of insertion of something, the intersection, let's say, into some other end-of-the-world brane boundary for the back theory, for the same back theory. And finally, another application of this intersecting end-of-the-world brane configurations is to explore networks of infinite distance limits at infinity moduli space. So this is a space-time, this is some moduli space like Calabi-Yau compactification. And in general, you can have here several scalars that correspond to are associated to the different end-of-the-world branes. And in here, they correspond to different infinite distance limits that define different divisors in your Calabi-Yau moduli space that typically can intersect. So basically, when you approach the intersection of the two end-of-the-world branes, you're approaching the intersection of the divisors that define the infinite distance limit of the two independent scalars that are associated to this. Okay? So for these networks, a typical example or template would be the Calabi-Yau case studied by Grimley and Paltic, for instance. Okay, so what we did together with Roberta and Adriana is to consider the general solutions of two intersecting end-of-the-world branes with two different parameters independent, delta 1 and delta 2, which look like that. Okay. So basically, we start with some theory, which is gravity coupled to two scalars with general potential, and we allowed also for some mixing term here, which turned out to be relevant. And then the metric contains two warp factors, which are kind of superimposing the warp factors of the two independent end-of-the-world branes. So it's kind of very close to harmonic superposition in a sense. There is a solution in the local sense that is very locally close to this intersection. The scalar behaves as two exponentials in the different combinations of the scalars. And then the scalars run with the two independent directions and the warp factors also with the two independent directions. And there are some, these are the delta 1 and delta 2, the coefficients for how things diverge as you approach this end of the world brane or the other. Okay. If you look at the sources which create this solution, what kind of object is hiding here, you can compute the effective tension and how it depends on moduli. And basically, you're superimposing two independent things. In particular, there is no delta source localized at the intersection. Okay? Just for comparison, Blumenhagen and collaborators studied things which contain a source here. So in our case, there is no specific source here, just superposition of two things that don't talk to each other always. Okay? Now, in this case, you can study the scaling relations between the distance in field space and in space-time and so on. And then you find a lot of interesting relations. So if you parameterize the path in some specific way, that is in which direction you're approaching the intersection, then you have some scaling relation with some delta intersection defined in terms of several combinations of the gammas that are related to the path and the deltas, which are related to how things diverge at the different end of the world branes. Okay. And this is the plot as you change the gammas from approaching in this direction to approaching in this direction, you interpolate between delta 1 and delta 2. Okay. So this is an interesting way to connect with the distance conjecture, and this would be some kind of overall approach. There is also some tempting connection with the convex Hull formulations of the distance conjecture, but let me skip that. Okay. So there are many examples that you can build, and as you can imagine, before I was seeing a lot of dynamical cobordisms. Now I see a lot of intersecting dynamical cobordisms, which haunted me. So there is one application which has to do with a particular configuration that we studied with Roberta and Matilda even before this intersecting brane paper. But because I'm running out of time, I think I will skip it. If someone is interested, I'll be happy to discuss. Okay. So let me just skip these few slides and go to the conclusions, which are that dynamical cobordisms are fun, they are everywhere, and several can appear all at once. So our next idea or next project is to continue exploring these setups, in particular to try to understand better the world volume dynamics of these objects via different mechanisms, anomaly inflow, how branes can end on end of the world branes, whatever. So if you're interested, become a dynamical cobordism pirate and see you at the end of the world. Thank you.